Okay, we are due. I think homework 2 is due today. Questions? Homework for chapter 2. Chapter 2 stuff.
Can we just go over here?
No, just a few.
Okay, let's start off with that. No, not that. Sorry. Start off with 1.
Yeah, so this is chapter 2 stuff. 1?
Yes.
Yeah. Which is?
Y is equal to, hold on, I got it. Let me tell you exactly.
dy over dx is equal to e to the x plus y.
So
dy dx is equal to?
E to the x plus y.
Plus y separately?
No, like just plus. No, oh yeah, separately, yeah.
And you need to verify that any constant c for the expression y is equal to x e to the power of x plus, big plus, c e to the little x is a solution of that differential equation we gave you first.
Okay. One number? 1 in section, I don't know.
2.2, yeah, we needed to look at
2.2?
Yes, the example 2.2.
Okay, so verify just means this solves that differential equation, right? So remember what solves means is if you assume y is equal to this thing, that equation is true. So basically to verify, all you have to do is check that this actually makes that equation true. So one way you can do it is by looking at each side and making sure they're the same. So for example, I can start off with the left-hand side. So I'm going to call this guy the left-hand side. And which I'm going to abbreviate LHS just for writing down. This side is the right-hand side. Which I'm going to call RHS when it comes up. Okay, so I'm looking at the left-hand side. The left-hand side is dy dx. Now if I'm assuming that my y is this guy, then what is dy dx?
E to the x plus x e to the x. Oh, wow. Plus
What?
c e to the, wow.
Okay, and so then I can't really simplify that really, so I'm going to just move on to the right-hand side. Right?
Yeah.
And so the right-hand side is e to the x plus y. Now assuming this is my y, and I plug it in here, what would I get? Just plug that guy in. So it's x e to the x plus c e to the x. That's what I had there.
That's it? It's so depressing.
Yeah,
Do you know
verified.
how long it
So
took
why
me to
did
do
this
this?
question use
No, it did. I'm just stupid. Okay, never mind. Let's move.
It's just saying verify that this equation is true if we pretend that that's the y.
I
So I'm
didn't
just
know-
going to plug it into that
I
equation.
didn't know like what he was asking, so I went to Symbol Lab, and it's like it's supposed to help you with your homework. And then I called my friend I've been had in college, and he's in Health 3, and he's like, "What is going on with you? Like your professor is messing with you." And I was like, "No, he's very serious." And then it gave me like some p is equal to something like this shit was crazy. Okay.
Yeah, I don't know what's going on, but that's how you do it.
That's it. Okay.
Check each side.
Okay, doke.
Right. So you assume that your y is this, basically. You assume
That's so easy.
y equals x e to the x plus c e to the x, and you want to show that with that assumption, this is true. So you find the derivative, you get something, and then you work out the right side, you get something else, and you have to show they're actually the same.
Okay.
Once they're the same, it's verified. So usually when they say verify,
Yeah.
it's because they know that this is a solution, they just want you to check it, which is what I just did. It is possible, for example, in a test, for them to ask, is it a solution? Like they didn't say verify, they say, is it?
Is that a hint?
Right? And then if you do it and they end up the same, then you can say, yeah, it's a solution. If something doesn't work here, you say, no, it's not a solution, you try to trick me. So you can do that. But yeah, once they say verify, it means that it's actually a solution. I remember in I don't know, a couple semesters ago, I asked a question like that. I said, verify that this is a solution. And then a lot of students concluded, it's not a solution. I'm like, no, I told you it was. I said, just verify. I know it's the answer. You just want to verify it.
No, it's bullshit.
And they're like, it's not the solution. Or you
They
try to
lie.
trick me. Like, everyone expects me to try to trick them for
It's
something. I
not,
don't
it's
know
not
why.
their fault. It's because you like to trick. Remember that quiz on the last quiz when you were like, how many years am I going to have money? And I was like, about 30 years. You know, you got 30 years left.
No,
And then you were
as
like,
long as I live. Yeah, I make bank. 'Cause, you know, I rob banks. Anyway, other questions?
I mean, it's pretty much negated the entire chapter because we needed help with one side. So
5? What does that say?
dy dx is equal to x minus y over x minus y over x plus y.
Okay.
And what do we have to do?
we had to verify that for any constant c is greater than or equal to 0, the expression y is equal to negative x plus the square root of everything that I'm about to say, 2x squared plus c.
Is a solution?
Yeah, the solution is that way.
Okay, so same idea. I'm going to assume
Oh, and then there's a b and a...
y is equal to this. Well, we'll get to the b
Okay.
after. Then, if I look at the left-hand side, that's just the derivative of the y with respect to x. Differentiate this, what do I get? Go, anytime, I'm ready. What?
Get the derivative of that.
Yes, find the derivative. What's the derivative?
-1
Minus 1
plus 1/2 times 2x plus c to the -1/2 times 4x plus
times, that's it,
That's it.
correct, right? So this is minus 1. The 2 would cancel this guy, so I get plus 2x over this guy, 2x squared plus c, right? Which I could write as, if I wanted to, minus radical of 2x squared plus c plus 2x all over radical this. I just combine it into one fraction, just because. So I know that that's my left-hand side. Now I want to see, does that actually equal the right-hand side? So I go over here and I look at the right-hand side, and this is x minus y over x plus y. So I'm just going to start putting things in. X minus my y is this. Over x plus that. So on top, I have x minus a minus x, which gives me 2x. Then I have minus this guy. Over, now I have x minus x, so that goes away, and I'm just left with that guy. Same thing as that. That's equal to the left-hand side, so verify. Right, because it's the same thing. Both sides of the equation agree, therefore the equation is true.
That's my reaction to everything, man. It's really sad.
Can you work it out too? Does that work?
Another way would be to actually solve this to get that as the answer, but in general, I'd probably give you a problem where that won't work because I'd want to test if you know how to verify. For example, this guy, the only technique we know is separable, but this is inseparable. So you wouldn't really know how to solve it otherwise. So that's why this verification technique is a very powerful thing. They throw the answer in your lap. You don't have to like solve it. You can verify that it's true. But yeah, when a question like this comes on a final or something like that, they always put something that you can't actually solve by hand. Okay, one more, maybe a different kind of problem. $25. Okay, what does that say?
A man wants to retire at age 65 and be able to draw $10,000 a year from retirement savings to supplement his Social Security income and employee retirement benefits. At retirement, he anticipates investing his savings in government securities that should return 5% a year compounded continuously. By repeating the arguments that led to equation 2.8 in parentheses, show that after retirement, the principal P of t in his account satisfies the ODE. So then dP over dt is equal to 0.5 p minus 10, where we have used units of $1,000.
0.05.
What?
0.05.
0.05.
Oh, yeah, 0.05.
Okay. So based on what I told you last time, you could come to this equation right away. Remember, it's dP dt equals Rp plus K, where K is how much you're either depositing or withdrawing. In this case, it's withdrawing, so it's minus, right? This would be the interest rate. That part in part A that says derive this equation, you don't really need to know that. I'm not going to ask you to do it. But basically, for part A, what they wanted you to say is something like, to derive this, it's like the delta P, how is it done? So you apply some interest rate to the P per unit time, minus you're subtracting 10 per unit time, and the idea is you divide both sides by delta T. And then you take the limit as delta t goes to 0, delta p over delta t. And that just actually is the definition of the derivative that gives you dp dt. And you take the limit of both sides, delta t goes to 0, of rp minus 10. But the thing is, there are no delta t's over here, so the limit doesn't do anything. You just end up with rp minus 10. And so, therefore, you get dp dt is equal to rp minus 10. So that's how they derived it in the book. You don't need to know that. I'm not going to ask you to derive it. However, moving on to part, because you could jump from here to here. Like in a test, I'd expect you to just write this down.
Really? I could do that. I'm really good at writing notes.
Yeah, so just start out with rp plus k, figure out what your r is, figure out what your k is, and that's it. So your k would be the 10,000. Because he's withdrawing it, it's negative. So you put minus 10, and the interest rate is 5%, which as a decimal is 0.05. That's your r. So they do. So I wouldn't ask you to derive it from scratch like they did that, but you should be able to. After reading that question, you should be able to write this down without them telling you what it is. Like with that question, I wouldn't give you this equation. I just describe the situation. I expect you to figure out this equation and then use it. Yeah, and it's always gonna. So compounded continuously stuff, you always start out with this rp plus k.
I had a question.
And that's interest rate. This is how much you're depositing or withdrawing at regular time intervals. Yeah.
So for the regular time intervals, like the t's that they mentioned, where do I put those in? I know this dt would be like the derivative of time. I'm not sure.
No, this would be it. Your p here is a function of time, right? It's p of t.
Okay.
Right. But there's no t present as a variable itself in this equation.
Okay. Do you want me to?
Yeah. So part B says.
Determine the general solution of parentheses 2.14 and find a formula for the solution with as yet undetermined initial value p of 0.
Okay, so p of 0, which is how much he starts with, we don't know, and we want to solve this differential equation. So we start with dp dt is equal to 0.05 p minus 10. How do I solve that? Factor out of 0.05. I'm left with p minus what? Yeah, but what's 10 over 0.05? 200. And then what? Divide by p minus 200. It's separable. So I put dp over p minus 200 is equal to 0.05 dt. And then we integrate. On this side, I would get ln of p minus 200. On that side, 0.05 t plus c. And then I want to solve for the p, so I'm going to e both sides. So then I would get p minus 200 is equal to c e to the point 0.05 t. So that my p is equal to c e to the point 0.05 t plus 200. And so now if I set the amount at 0 is equal to p0, then that gives me, this is p0 when time is 0, and I solve for c. So this means my c in this case is going to be p0 minus 200. And so I'm going to go back and plug it in here. And I would end up with p is equal to p0 minus 200 e to the point 0.05 t plus 200. And that's the answer to part B. So you'll notice that the answer has a value that you're not sure what it is. You just call it p0. Part C.
It says, how large must the man's initial retirement savings be so that he can continue drawing his $10,000 income annuity for 20 years?
Okay, so here they're asking you to find p0 such that you can be withdrawing $10,000 a year for 20 years. So how do we set that up? He wants to be able to withdraw his $10,000 for 20 years.
T is equal to 20.
So if t is equal to 20, after 20 years, what should happen?
P should be equal to some other
P should be 0, right? He wants to be able to withdraw money until when the clock hits 20 years, there's no money left because he withdrew everything. So at t equals 20 years, P should be 0. That's at that point, you won't have any more money to withdraw. So this means you're going to have 0 is equal to P0 minus 200 e to the point 0.05 times 20 plus 200. And now you're going to solve for P naught to make that happen. And you can see in general, you could have figured out how much you have to deposit initially to last for any amount of time. If you want it to last for 30 years, you put 30 here. For 40 years, you put 40, 50, you put 50, so on and so forth. How do I solve for that P naught?
Subtract 200.
Move 200 to the other side, so I have minus 200 equals to P naught minus 200 e to the point 0, well, 0.05 times 20 is what?
1.
Just 1.
So then divide by E.
So this means I have minus 200 over E is equal to P0 minus 200. And so my P naught is 200 minus 200 over E, which is approximately what? What?
The entire answer you want?
The entire answer, yes. 126.4. So P0 would be $126.4 thousand.
Oh.
Right, remember it's in units of thousands.
So this is saying after 20 years?
$126,000.
Yeah?
After 20 years?
Yeah.
You multiply 9 by 1,000, is that okay? Or
Yeah, it's 1,000. Yeah, so that's the initial you'd have to deposit to be able to do that for 20 years.
Why is it so expensive?
would you make this an exam question?
Hmm?
Would you make this an exam question?
The 25 is a pretty fair exam question, except for part A, I wouldn't ask you to do it that way.
What part do you do?
Part B and C are totally correct. Okay, can pass the homework up. We are going to continue with chapter 3.
Jhevon, do you want number 2, the Excel?
Yeah.
Okay. And do you want all of them stable even though they're different homework numbers?
I want them stable according to the syllabus, how the topics are.
Okay.
This stuff.
Today?
Yes. Oh, which reminds me, the exam. Our first exam is after chapter 3. So when you finish chapter 3, like a week after that, you have the first exam.
So we'll finish chapter 3 today, right?
Probably, yeah.
So Wednesday's going to be like a review session mostly?
No.
This week?
What are we going to do
Wait,
Wednesday?
wait. Hold up, are you saying that the exam is on Wednesday?
No, the exam's going to be next Monday.
Oh.
If I finish it now, it's going to be on Monday.
So what are we going to do Wednesday exactly?
We are going to continue.
Chapter 4.
You're
No
going to keep
review?
moving. No, you do the review problems on your own. The review problems are already on my website. Practice them on your own. If you need help, go to the tutoring center or ask a friend or something.
For your exams on both of these, yeah.
Are my exams what?
Your old exams on both.
No. But you are to practice from old exams. They're not mine, but they're going to be very similar. Okay. So last time we talked about an equation in theorem 3.2. What was the equation that you had to write on the quiz?
F of x plus delta x
Oh my god, I think I wrote that one.
Oh, it's plus?
approximate to f of x plus f prime of x plus delta x divided by 2 times delta x.
Right. This was theorem 3.2. It's the equation that we will be using in modified Euler's equation. It comes from taking an extra half step in the middle of when you're approximating something. So it's like extra Euler equation within an Euler equation. Well, that's basically what's going on. So we find the slope somewhere halfway between our steps up. So, and we introduced that last time. We didn't really do anything with it, but that equation will tell you everything you need to know. Maybe I can look at one of these quizzes. So in the quiz, well, did I actually do an example like this? No, I'm not going to do an example, so I'll probably just mention it. So in the quiz, for example, how would you use this? So if I look at quiz version B, which I'll post the answers tonight, we were given that our y prime is equal to x cubed plus 3 plus e to the y. And I gave you two pieces of information. There's an initial condition, y of 0 equals 0. And we know that y of 0.1 is approximately 0.4. And I asked you to approximate y of 0.2 using this equation. So based on this guy, what is our x and what is our delta x for this equation, for this problem?
X is 0,
X is 0 and
0.2.
this would be 0.2. Okay, so this gives us the following equation. If I use that guy, I know that y of 0.2 is approximately equal to y of 0 plus y prime of 0 plus 0.2 over 2 times delta x, which is 0.2. Now y of 0 we already know, that's given, right? So now the question becomes, this would be y prime of 0.1, right? So this I have given, that's an initial condition. That's just 0.2. The question is, what is this guy? How would I find y prime of 0.1?
Substitute it to y prime.
Right, use the only other piece of information we haven't used so far. I told you what y of 0.1 is, and I told you what the derivative is for a particular y value. So to figure this out, use the y prime. Y prime of 0.1 is what I get when I plug in 0.1 for x. And the y, I would plug in 0.4.
Oh, I did that. I didn't like do that.
Right? And so, what is that? 4.49. What? 3. So then, ultimately, my y of 0.2 is approximately y of 0, which is 0, plus this, which is that, 4.493 times 0.2, which is 0.899. So that's sort of how we're going to be using this guy. I'm going to show you another way to do this in a table, but that's basically it. So notice in the question, I had to tell you what this guy was. In general, what you're going to have to do is, this guy, you would figure out using the regular Euler's formula to use it in this one. Okay, so.
We don't need. No, it's okay. I just wanted to copy all of them.
Okay.
You can start it with now. I wrote most of it. So 24.
So now let's use theorem 3.2 to approximate this guy, radical of 25.1. We did this with theorem 3.1. I want to use theorem 3.2 to approximate that now, so you can sort of compare the two, how good one answer is versus the other. So again, we're going to have to figure out what our f or our y is. F of x, what would I choose here? Radical x, right? Because I want to approximate a radical. F prime would be 1 over 2 radical x. Right? And so now I also know that my x is blah and my delta x is another blah. What is my x? It will be 25. X is the nice number. Delta x would be 0.1. This means by theorem 3.2, to approximate my f of 25.1, this is approximately equal to f of 25 plus f prime of 25 plus 0.1 over 2 times my delta x, which is 0.1. So basically, this is f of 25 plus f prime of, this would be 25.05 times 0.1. Now this guy we know, f of 25, we just use this guy, right? F of 25 is 5 plus what is f prime of 25.05?
That's funny.
Right, so let's look at f prime. So let's this guy. Let him sit here for a while. We're going to come back to that. Let's go figure him out and then we'll come back to there. So at this point we have, let's figure out f prime of 25.05, right? Which basically is 1 over 2 times the radical of 25.05. That's what I want to figure out, right? Now see, what I'm going to do here is I'm going to approximate this guy using theorem 3.1. Which I believe we actually did that before. Yeah, we did approximate that before using theorem 3.1. So last time I did theorem 3.1, example B, what did we get? We did this. Huh?
We did this problem before.
Yeah, this one. Using theorem 3.1, we approximated that. 5.005. Okay. So this means my f prime of 25.05 is approximately 1 over 2 times 5.005. And what's that? .099. What? Give me some more. And then 3 zeros? Okay. Okay, so now that we have that, we come back here, we plug this in. So we're going to have 0.099900. Let's leave that off. Times 0.1. So this is approximately equal to what? 5 point, what's that? 0.00999. And that's our approximation according to theorem 3.2. And you may have noticed that that's actually I don't remember, what did we get for this when we used regular Euler's method? The theorem 3.1, when we did this guy, what did we get? That's example A when we did the first one. 5.01, right? And the actual answer when we plugged into our calculators was 5.009990002. Remember that? And remember we had a bunch of zeros here missing? There were 3 zeros, right? Dot, dot, dot. Which means with this theorem 3.2, I was actually correct up to 1, 2, 3, 4, 5, 6, 7 decimal places. Whereas with theorem 3.1, I was only correct up to 2 decimal places, right? 7 decimal places, right? I'm within a millionth, or within 10 millionth of the answer, right? So that's why it's a very powerful technique, and it really magnifies how accurate you are. But one thing you'll notice here is that when you start to do theorem 3.2, you get to a point where you find something that you don't know what it is. You use theorem 3.1 to figure that out. Then you come back and plug it in. Right? So this one has a little back and forth. Right? Like in the middle step, we use the regular Euler's formula, theorem 3.1, to figure that out. And then once we figure that out, we plug it back in and then we can continue. So this modified Euler's technique has an Euler built into it, right? So it's sort of different in that way. But as you can see, it's worth it. Like I've gotten so much more accurate. Yeah.
I mean, it's cool and all, but like, we did it with the calculator, so we needed the calculator to do it, right? So why can't we just stick 5 to the square root of 25.1 in the calculator, like in biology? You know?
What, you mean to just do this without approximating it? So here's the thing. Right now, I'm doing something as simple like approximating this. Now sure, if you wanted to do this, you plug it into a calculator. But the principle is, a lot of times when you're doing research, you're not just figuring out one little number. You're looking at tons of different variables, tons of numbers, all at the same time, right? Now a computer can handle that, but then you plug it into a computer and you give it like 1,000 tasks to do where each of them has 1,000 rows or even more. Computing time slows down. There's actually a form that tells you how long computing rate goes. It actually compounds on itself, right? So it's like, with just a few variables, it takes this long, but then add a few more variables, and it takes this long, and then this long. Your computer can quickly run out of processing power if you're processing large amounts of data, right? So if you're just plugging in an actual function in your computer, like a square root of x, versus plugging in something that looks like y equals mx plus b, a straight line, this will in general, if you're doing this computation over and over, especially with a function that's super complicated, it will actually slow down your computer a lot, and it will cause problems.
It's the same for a brain.
So the idea is,
Yeah, my brain
My
would be
brain
the
dead.
idea is the approximation would even help a computer, right? If you're computing one little number, it's not a big deal. But usually when you're using a computer, that's not what you're doing. You're large masses of data, like huge masses of data.
That's if you're like
And you're
your
asking a
smart
computer.
level. My smart level, I need that calculator.
Yeah, but
But it's
yeah,
cool.
try to plug into a calculator 10,000 times,
Oh.
50,000 times, 1,000,000 times. Right, a lot of these things, when you're looking at like the studies that people do, and you're following people like over 10 years, you're doing this health study, right? You don't just pick a couple people and just run a couple numbers, right? You pick thousands and thousands of people. You take 10,000 people and you follow them for like 10 years of their life to study the effects of smoking. And you're keeping all these numbers, right? Every few months, these people get a checkup and you record a number. Pretty soon you have a large masses of data, and now you're going to throw into your calculator this random function that's supposed to measure like cancer growth or whatever, and it's this really complicated function. You say, computer, here, compute this 1,000,000 times. You're going to be sitting there forever, right? But if you convert it to a straight line, computer, figure this out, y equals mx plus b 1,000,000 times. No problem. 5 seconds, done, right? So even with a computer, this actually helps you out, right? So it does cut down on computing time for both humans and computers. So processing time is a huge deal when talking about computers. The more you can cut things down so that you don't have to compute as complex things, the better it is for you. So it's just like, yeah.
Question. So why didn't you put 25.05 into this f prime?
Into which f prime?
Yeah.
I did put it in that f prime. It's the same thing. 1/2 radical block. 1/2 radical block.
X was our law.
Yeah.
Well, you used 3.1. What do you mean?
Yeah, because how would I have known what this was otherwise? Right? I couldn't use 3.2 because 3.2 keeps telling me to use 3.1. It's like built in.
Okay.
Remember when I was explaining the concept? You had this curve. You started over here. Then halfway through, you measure another tangent line, remember? We started out with one tangent line, and then we measured another tangent line to get to the end point. So the idea is, in the middle, you have to know what your y value is, but the idea is you don't know what your y value is because you started off with an approximation. So you can only approximate what that y value is in the first place. And so to do that middle approximation, use theorem 3.1. But yeah, of course, what I'm showing you here is stuff that I could do by hand and show you on the board. In real life, it's not going to be this easy to just, you can just plug that in your calculator. It's not going to be like that. You're going to have large masses of data. And you're going to want your computer to be running as efficiently as possible and as fast as possible. Especially if you're doing computations in cases of emergency, like some worldwide pandemic hits, right? You're going to want to know answers fast. You don't want your computer struggling computing 1,000,000 square roots
No,
when
once
you could
that
just be
pandemic
running on
hits,
it.
I'm going to Hawaii. Y'all can figure it out yourselves.
Yeah, you're going to go to Hawaii and run this on a computer and figure out the numbers. Like, where's this thing coming from? What's going to happen? How many people are being infected per day? Right? So there is merit to this, even in the computer age. So don't think there isn't.
It's a fabulous series.
Yeah, so now that we've actually done that by hand, I'm going to show you the tab table method of doing this. This is called modified Euler's network. So this is going to take Euler's method and add an extra step into it, but we'll get there twice as fast by doing this, right? So here's how your table looks. So it's actually a longer table. Do I have space for this? So your delta x and all that stuff is computed in exactly the same way. And you start out pretty much the same. Right, so here's your x, here's your y, here's your y prime. Right? So again, delta x equals b minus a over n, just as normal. And we're assuming that y of a equals c, and we want to approximate y of b. So you start out the same, right? So your initial x value is your a, your initial y value is your c, and then in this guy, you plug in x and y into the y prime formula. So far, so good. And that you're going to be doing all the time, right? Every time you're doing a derivative, the given y prime formula is what you're going to use to find the derivatives. Now here's where the modified starts to make a difference. You're going to have to do this again for the half step, the midway point. The notation they use is x half, y a half, and let me make more space here. So I'm going to write in words how to compute this. Y a half and y prime a half. Right? So now our table is going to have 6 columns instead of 3 because I'm computing in the half step. Right? This guy is basically exactly the same as your f prime of x plus delta x over 2. That's what this guy is. Right? That's what we're going to be using. Okay? So here's the process. Given an initial condition, put it here, plug into your derivative formula, you get the value here. Then you're going to move here. What is x of a half? It's the x value you get by taking half of delta x step. So remember, for these, you keep adding delta x. So it's x old plus delta x, and you keep doing that until you hit b. Right? Keep adding delta x. Here, you're going to have x old plus delta x over 2. You're adding the half step, right? And you're going to continue doing that, right? So x is taking the full delta x steps, going over. This guy's just stepping half the distance at any given time, right? Your y value is sort of like what I'm going to need to figure out here. I'm going to use theorem 3.1, right? So here I'm going to use theorem 3.1. But now I'm going to use it with a half step, with delta x over 2. In other words, I'm going to always be using the formula y old plus y prime old times delta x over 2. And I'm going to keep filling that in. here, I'm going to plug in x half and y half into derivative formula. And I'm going to keep doing that. Where things start to change is in this y. Now, ultimately, to compute the new y, that's where you're going to use theorem 3.2. From here onwards, you're going to use theorem 3.2. So you're going to take the y old plus the y prime half old times delta x. Right? This is like your f of 0, f of x plus delta x. This is like your f of x. This is like your f prime of x plus delta x over 2, which is that guy we're computing over there, times your delta x. Okay? That's sort of the idea that we're doing. So this you have to write down because you have to memorize doing this. So again, start off here. The good thing is the y prime columns, they're easy. They're always the same thing. The given form that you're given, you plug in into these guys. So to find y prime, you plug in the x and y into the given formula. To find y half prime, you plug in the x a half, y half into the given formula. Right? So to find the y prime, you're always plugging in the two numbers to the left. Right? To compute the y half, you use theorem 3.1, but instead of using delta x, you use delta x over 2. You take a half step. And then to find y's, every y except the first one, you're going to use theorem 3.2. So you're using the old y, but the derivative you're using is going to be the one all the way from that. Right? This derivative is the one you're going to be using. Okay. So copy that down, and I'll actually run through an example with you so you can see how it's being used. So it's a lot longer than Euler's method, but if you do a few examples, it'll start to become second nature. Again, the errors with actually plugging stuff into your calculator gets multiplied here, right? There's a lot more chances for mistakes, so make sure you do your calculator properly. Use your calculator properly, don't just make mistakes, because that's where it all can go to get crazy. Because remember, in this guy, every step depends on the previous step. So if you make a mistake early here, it's just going to go through the whole thing and mess everything. So you have to really be careful when you're plugging these guys in. So just remember, y prime, you're always plugging in x and y. Y half prime, you're plugging in x half, y half. Theorem 3.1 is used in this column with delta x over 2 instead of delta x. And theorem 3.2 is used in this column with your old y and this y prime. And that's how you fill up the table. The x's are filled up similarly. The x's are usually no problem. Everyone usually gets the x's. So that's the x's. So you keep adding delta x here. You keep adding delta x over 2 here. And that's done. So are we done copying? Okay. Let's actually run through an example. Yeah, so again, I'm going to redo an example that I used the regular Euler's method on, and we're going to compare our answers. So we can see how close we actually get with this method versus the other one. So last time we used Euler's method with 4 steps to do this thing, or I think we used 5. Yeah, I think we used 5, right? Now I'm going to use only 2, and we're going to see how it. I don't remember if we used 4 or 5. Okay, so here's what the question is going to look like. Use the modified Euler's method. with n equals 2 to approximate the solution to y prime equals x divided by y of 0 equals 2 at x equals 1. In other words, I told you what it is when x equals 0. I want you to tell me what it is when x equals 1. That's pretty much a typical way to phrase the question. So the question was specifically asked for modified Euler's method or Euler's method. So you read the question very carefully so you know which one you should be doing. So here I told you I'm going to use 2 steps. And this is what I want to approximate the solution to this differential equation with that initial condition. So let's do it. And here. So here's my x. I don't know how much space we're going to need. Here's my y. The y prime. So my x half. Y half, y prime. All right, so those are always going to be the numbers. Okay, so with x's, we're going to start at the, let's figure out the guys here. So what's my delta x?
It's a 1 minus 0 divided by 2.
So it's 0.5, right? So here, my initial is 0. I always start with 0. Then I'm going to keep adding delta x. So at 0 plus delta x is 0.5. 0.5 plus delta x gets me that 1. Okay, let's figure out the other guys. What's the y?
Y0 is given.
Yeah, so what is it?
2.
So it's just 2, right? When x is 0, my y is 2. No problem. Move over to here. What's my y prime?
Plug into the formula. So
Right, you plug in the x and y into the given derivative formula, so you're going to get what?
1/2. It's 0.
0. X is 0, y is 2. This
no.
gives x over y, so it's 0 over 2. Just get 0. Now what's your x a half? Your delta x is 0.5, which means your x half is 0.25. You're always adding half the delta x. So here's going to be 0.25.
0 is 0.25.
Y1.
And then what would the next one be? We can actually figure out the x's right away. 0.75,
Okay.
right? So it starts out with a half step, but then it goes by delta x, and so you can do that. We're not going to need to know this. Remember, the guy we're after is the guy that's going to end up here. So once we figure that out, we don't need to go any further. So I don't really care about these guys, which is why in like a quiz I mark these out, because you really don't need to know them. We want to figure out the number that's going to end up here. Okay, so here, x's is normal. You plug in the first one, keep adding delta x to get here. For the x half, you add half the delta x and keep adding that, right? You keep adding half the delta x to this number. And that gives you the x columns. So those are usually no problem. Now that I have 0 and 2, I plug that into the y prime formula to get this. Here's my x a half. Now how do I find my y half?
Is it 1?
Isn't it 2.25?
Right, so now I'm going to use theorem 3.1, right, remember? In this column, theorem 3.1 with delta x over 2, which means I'm going to take the y old plus the y prime old times delta x over 2. My old y is 2 plus my old y prime is 0 times delta x over 2 is 0.25. So this one is 2. What is my y prime a half?
Is your half 0.25 divided by 20
By 2. Right? For this one, I'm just going to use the given derivative formula with this x and y. Right? The halves always go together. Right? So I'm going to take the x divided by the y, and that would be what?
0.125.
125. Now here onwards, I'm going to be using theorem 3.2. I'm going to take the y old plus the y prime half old times delta x. What's my old y? 2 was the previous y value, plus my old y prime half was the guy all the way from over there. So that's going to be 0.125 times delta x, which is 0.5. And what is that?
$2.0625.
2.0625. What goes here?
Over 2.0625.
Yeah, and what is that?
0.242424 repeating, so 2.4.
2424.
Yeah, just repeating 2.4.
Don't just copy. Try this in your calculator while we're doing it, so you're getting the same numbers to make sure that you can actually do it. Okay. How do I find this one?
So it's 2.0625
Plus
25. No. Oh, 2.2424.
plus 0.2424 times 0.25. What is that? $2.123. 2.123.
106.
Okay, how do I find this one?
Divided by 2.1. No. Something divided by 2.123.
0.75 divided by 2.1231 gives me
0.3533.
now we come back over here. What do I put here?
$2.0625.
2.0625.
Plus 0.3533
0.3533
times 1
times 0.5.
times 0.5.
And then that would actually give me what?
it's 2.2395.
2.239.
15, so 9
So from this, that would be your approximation. Y of 1 is approximately 2.2392. So this process is significantly more long-winded than the last one, so let's recap on exactly what happened. So you should be trying this, making sure you're getting the same numbers. Everyone should be getting the same numbers. So I'm given a differential equation with initial condition, which means I know what its value is at a certain point. I want to approximate its value at some future point. Okay? And I'm told I want modified Euler's method, which means my table should have 6 columns. X, Y, Y prime, X half, Y prime half. Okay. Now, as always, I'm going to need to know what my delta X is. It's very important. So remember, my delta X is B minus A over N. The A and B are the X values, remember, right? So B is my final X value, A is my initial X value, N is the number of subintervals, which I told you. Okay? So the final X value is 1, the initial X value is 0. So I do 1 minus 0 over n. That gives me 0.5. Once I have that, I can fill out my x columns right away without thinking about it too much. I start with the 0, which is the initial, and I keep adding that number. So 0 plus 0.5 plus 0.5, and I keep going, right? If I had to, right? Same thing here. I keep adding half a delta x to that x value. So a half step over, halfway between 0.5, I'm going to get 0.25, then 0.75, and I would keep going if I had to, right? So I keep adding a half delta x to that. Or you can just add a delta x over 2 to that one, and then the difference between this and each successive one is also delta x, right? So I can keep adding 0.5 once I get to the first one. Okay. But that's the x columns all filled out. Those you can fill out right away, and doesn't matter what the functions look like, these values will always be set up that way. Okay. Now, for the first y value, that comes from your initial condition. When x is 0, y is 2. So x is 0, y is 2. To figure out the derivative, for both derivative columns, you always do the same thing. You plug in the x and y into the given formula. In this case, the given formula was x divided by y. So at any given time, I kept dividing x over y, x over y, x over y. I kept following that same formula. For this y prime, I use that x and that y. For this y prime, I use this x and this y. Right? But I keep plugging into the same given formula, x over y, x over y, x over y. Right? So for my derivative columns, I'm always using the given formula. Right? And I'm plugging in the corresponding x's and y's. Okay? So that takes care of the x columns and the derivative columns. Right? Now the two strange guys are these two columns. In this one, you're always using theorem 3.2. In this one, you're always using theorem 3.1 with delta x over 2. Or you can just memorize the formulas that you're using in each column. Right? Y old plus y prime old times delta x over 2 is always the formula you'll be using there. And y old plus y prime half old times delta x will always be the formula you're using here. It's always going to be the same thing. It's a repetitive process, right? Called a reader process. Okay. So here you're always going to take the old y value, which is from here, plus the old y prime value times delta x over 2, right? Which in this case is 0.25. There were 0.2 here, but that should have been a 0.25. Okay, and I get that. And I will always be doing that. Take the old value, I'd always take this value plus this times delta over 2. That's always what I'm going to be putting here. Right? When I end up here, I'm always going to be using theorem 3.2. Right? I'm always going to take the old y value, which is the guy from above, plus the y prime half, which is the guy from the last column, times delta x, which you found in the beginning. Right? And you're always going to be doing that formula. You're going to keep repeating this until it's done. Right? And you keep going for however many times they tell you. Now with modified Euler, very typical to only use 2 steps, so I'm going to ask you for 2 steps. I won't ask you to do this more than twice. I'm not a sadist.
Jhevon,
Yes.
isn't this theorem 3.1? It's not like that one.
No.
Y O plus
The thing
Y
that
O.
doesn't make it theorem 3.1 is the y prime half. It's not just a regular y prime. It's the y prime half. This guy represents the prime of x plus delta x over 2. That's what this guy is. Right? Okay. But once you realize that this is always the formula you're going to be using in this column, this is always the formula you're going to be using in this column. Y old always refers to the previous value from this column. That's basically it. Any questions?
Okay, for the x half column, 0.25, we're looking between like 0 and 0.5, and then 0.75 is obviously between 0.5 and 1, right? That's how we do it?
Yes, we're taking half a step. Remember, our full step size is 0.5.
Okay.
Here I'm only stepping halfway, right?
Yeah.
So halfway between 0 and 0.5 is 0.25. And then I just keep taking back numbers, right? Halfway between 0.5 and 1 is 0.75. Just think of it here, once you have this guy, add half of delta x to it, you would get this guy,
Yeah.
and then you keep adding delta x.
Got it.
So it's always just 1/2 step between this and the next value. Halfway between 0 and 0.5 is this, halfway between 0.5 and 1 is this, and so on and so forth. Any other questions? So, yeah, it seems daunting in the beginning, but if you really run through it and you sort of memorize the steps, it's just a matter. The most you have to worry about here, hopefully if you study correctly, is plugging things in your calculator wrong, so which is where you're going to spend most of your time.
Now on an exam, in terms of this table, do we have to remember that it's x, y, y prime, x half, y half? Do you know what I'm saying? Like, do we have to remember the labels?
I would, yes. Yes, you have to label the top,
Okay.
but I would.
And you will always give us n.
Yeah. I'll give you n, or I'll tell you how to approximate. I'll either tell you what delta x is directly, or I'll tell you how many subintervals are. But yes, a general rule of thumb, this is pretty much a standard way to set things up, but a general rule of thumb, in a math class, if you're always using a formula, you always want to set things out the same way, right? Like all the time. Like every time you're practicing, you do it the same way in your homework, the same way in your quiz, the same way in your test. You always practice the same thing. Because what happens is, one thing that happens with students sometimes is, you know, that phenomenon where they're like, I just blanked out, or I knew this, but I don't know what happened, or I thought I did better than that. What happened is, because you arrange things differently all the time, it sort of confuses your brain a little bit. So when it goes in freak out mode, it doesn't really know what to do, right? As opposed to, if you're always doing the same thing, it becomes sort of a muscle memory. It's like your hands remember what to do instead of your brain. So even when you're in freak out mode, you automatically know what to do next, right? It's kind of the same therapy that you know, if you go into like the Marines or something, they blindfold have you assemble your rifle, right? And just keep doing that over and over. You always do it in the same order with the same pieces all the time. Why do you do that? So when you're freaking out, there are bombs going off all around you and people are trying to kill you, you can assemble your weapon without even thinking about it, right? It's the same idea. Always set something up exactly the same way. Every time you have a method, always practice the steps in exactly the same order, in exactly the same way. So when you go into a test and you start freaking out, your hands are just going to be right under them. Right? That's, you laugh, but it's true. Right? Sometimes you just get into like a habit of doing something, and that actually is what saves you.
So my first chem test is on Monday. Can we have our test on Wednesday?
No, because we have a bio test on Thursday.
The bio really easy. I can put it in the
Yeah, okay.
Chem is wild. I don't know.
It's Monday. So this ends chapter 3. So test 1 is on Monday, a week from today. On my website, there are review problems for test 1. You'll see them. Review problems for test 1. Go through them. You can go to the tutoring center if you need help with them. But make sure you try to get I guess we'll stop there. Yes. Chapter 3 homework is also due Wednesday. Yes.
That day was the longest day of my life.